So, hello everyone. This question is from Razavi sir textbook, design of analog CMOS integrated circuit. So, uh, first analyze yourself. Like we have to plot this Vy and Vx. So let's analyze. Okay. So, in this, all transistors are identical. I also did the LTspice simulation for the later verification. So you will get a clear understanding of the question. So there are three time phrase like t less than 0 and t is equal to 0 plus and t greater than 0, or we can say t at infinite. So there are three time phases. Like first to analyze for t is equals to t less than 0. At t less than 0, we assume that there is no reference current, like in simulator as well. When you simulate that, it will uh, assume that there is no IRF current. So we are assuming that there is no IRF, and for it, and we can say there is M2 and M1. If there is no IRF, M2 and M1 are in not in a current mirror configuration. So there is no current in, like if there is no current in M2, there is no current in M1, and if there is no current in M1, there is no current in M3 as well. So uh, So we can say for Vy, first we will see by Vy, for Vy. So for Vy, if there is no current at time is equal to time less than 0 time frame, then Vy is equals to at VDD. As there is no current in this branch R1, there is no voltage drop in R1. If there is no voltage drop, that Vy, then Vy will attain VDD. So at t less than 0, Vy will become Vdd, and let's analyze for Vx. And for the Vx part, first, first there is a constant V bias voltage, and if there is a V bias and V bias is for V bias is Vb is Vb is therefore to bias the bias bias the MOSFET M3 in saturation. Like it's a default case, like we apply V bias to any MOSFET to make it in operate in saturation region. So this is kind of a default case, or we can assume this will as this as well. So in the in saturation, there is a current flow in 3 ID. Let and But we assume that we didn't assume, like we can conclude that there is no current flowing in M3 as well. But let's suppose if there is current, then that current will be ID, which is drain current ID3, and which will equal to half mu n c over x VGS minus VTH whole square. This was the current saturation current. If V bias is there, and V bias will make M3 in saturation. So these were our conclusion. And but uh, uh, let's say uh, let's, let's solve this. Like it will become 2ID3 and mu and c over x under root plus this VTH will come here, and this VTH is VTH3 will become VGS3, and we are analyzing for Vx, and VGS3 is equals to VB, as gate voltage is VB and source voltage of M3 is Vx. So we can find Vx from there. So from here Vx will look like this. Vx is equals to VB minus VTH3 minus this component 2ID B1 C over X. This was our equation. But for t less than 0 time frame, we are assuming that ID is 0, ID3 is 0. So this whole component will become 0. But for this time frame, which is t less than 0, that our Vx has some potential, that we can see this in simulator as well. and which is VB minus V threshold of 3. So this was our initial Vx where there is no biasing current. Now and for this Vx is VB minus V TH3 and V by is equals to VD. So this was our conclusion for this part. Now move to the second time frame, which is at t is equals to 0 plus phase. Like, let me copy the question again, which is, if it's yes, Control C. So for this time frame, t is equals to 0 plus time frame. Now uh, that and in the question that V capacitor, we see 0 minus, and 0 minus is 0, and the capacitor doesn't change voltage is instantly. Like a change in voltage will opposed by the capacitor. So we see 0 plus as well is 0 volt. So for this instance, for t is equals to 0 plus instant, that V source of 1 of the MOSFET is equals to VC of 1, which is 0. Like, it is kind of a ground condition. And if this is ground, so for the current period condition, that uh, we get gate voltage of two MOSFET and source voltage of these two MOSFET will have to be equal. And for this time instance, that M2 and M1 will behave like a current mirror, will behave like a current mirror. So this M1, this M2 will try to push current IREF, will try to push current IREF into M1. Okay, as for this instant, this circuit will behave like as a current mirror. So this M1 will pass IREF, and for this time being, and there is one more thing. Like, if this is a constant step current IREF, and for this instant at is equals 0 plus, if this IREF current flow is M1, this same current will flow in this capacitor, which is C1. So there is a constant current charging a capacitor. So what will the voltage rise of this capacitor? So for this timing, as VC1, as the voltage equation of any capacitor will look like this. This is C, and this is I dt. And for the step current, this will become this will sorry, it is a constant current. Constant current. If we integrate this constant current, we will get a instant jump in the voltage of the capacitor. Instant jump. So for this time frame t is equals to 0 plus, the IREF current will IREF current will become like a infinite current, as this is an instant current. So for this time being, uh, the current will jump, the voltage of capacitor will jump instantly from 0 volt to some specific volt, as it look like IREF look like as IREF looks like a step current, but it's not a case for t is equals to 0 plus, as t is equals to 0 plus is very short period of time. So we can say it is like impulse current for this time frame. And if we integrate the impulse, we get a step our waveform. So for this time frame, capacitor voltage jump instantly from 0 volt to some specific volt. This can we can we can see this as well in the simulation. So there is some ICT, I by C, some constant I by C, and but for the whole period of time, it is like a step current. So we integrate step, we will get our ramp. But for this there is for this is for this case this is not true, like we will see later. But for the time being, for t is equal to 0 plus, we can say that our vc is 0 when t is t less than 0. But whenever these two MOSFET will become as a current mirror, then there is a step, there is impulse current flow in the capacitor, not impulse, but for this timing we can say this was an impulse. And and due to this equation we can say that our voltage rise from 0 to some specific volt. So for timing we can say there is some potential buildup in this state, like we there is something potential, like we can see this as well in the simulator. Now, now uh, let let's move to the next analysis. Now VC is rising. VC1 is VC1 is rising. So VC1 is VS1, and if VC1 rising, that VS1 is as well rising. Now for this time, now for this that VS1 is not equal to VS2. So these two MOSFET M2 and M1 will not behave as a current mirror, but this gate voltage is fixed by this current mirror M2. So we will see this, we will use this later. How analysis, analysis is that VC1 increases, VC1 increases. And before that, one more thing, like that if VC, if M2 and M1 is not in such current mirror, but for time being, like VC1 is not much that it will make this M1 in triode region or off region. So we can assume that for the time being, the this for this analysis we can assume that M1 and M1 is in saturation, not in triode region, not in off state. So we assume this, that our MOSFET M1 is in saturation, but it is not a current mirror with M2. Are you getting my point? Like it caused the VC1 voltage is not much high that it can make this M2 out of saturation and push to it a triode region or offset. So this is my point. Okay, so VC1 is increasing. If VC1 increasing, that VG VGS1 of VGS1 is decreasing, like as VG1 is fixed and VS1 is VC1. So VC1 is increasing, that overall VGS1 is decreasing, and the current and the MOSFET M1 in saturation. So for this for this for the current equation, like what is the current equation, which is half mu n C over x and C over x C over x W over L VGS minus VTH whole square. So if VGS1 is decreasing, then our also ID also decrease. So our ID1 decreases, and if ID1 is decreasing, ID3, which is the same current, ID3 and ID1 is same current, so ID3 will also decrease. And if ID3 will decrease, if ID3 will decrease, that due to this our Vx will also decrease. Like how we can see in this, that our Vx will depend on ID3, and for time t is greater than 0 or greater than 0, we can say that our ID3 is decrease as we prove in this statement, as VC1 decrease, VGS1 decreasing, and ID1 decreasing. So ID3 is also decreasing. So due to this, our Vx is also decreased, as this equation state, as ID3 is decreasing, this whole component will decrease. And if this whole component will decrease, it will become much more smaller and smaller. So this uh, as this is constant and this is constant. So due to this, our Vx will increase as this component will decrease, as this is in under root as well. So my point is, like, as ID3 decrease, Vx will increase. This is the conclusion for this analysis. So Vx increase. So the main conclusion is this, that Vx will follow Vc1, as Vc1 increases. As Vc1 increases, that Vx1 also increase. This is our conclusion. So Vx will follow Vc1, but there is always a catch, that our Vx will always be greater than Vc1 or uh, Vc1. So why this is the case, as uh, any MOSFET which is working in saturation or triode region, any MOSFET which is working in saturation in triode region. Let's see this M1 MOSFET. If it has to working, it has to be in saturation or triode region, and there is two condition for there is one condition for to MOSFET to be on, as in saturation and triode region. In both of the region, MOSFET has to be on. So for the condition of on condition is VDS, on condition is VDS is always greater than 0. This is the on condition for any MOSFET. There is one more on condition, which is VGS is greater than VTH. This is also a home condition for MOSFET. So, but our point of interest is this one, as VD is Vx and Vs is Vc1, which is greater than 0. So we can say that Vx is always Vc1 when MOSFET is on, and in on condition MOSFET will work in either in saturation or either in triode region. So this is my point. Like, as VC1 increase, Vx will increase. So Vx is following VC1, but which is larger and which is smaller. That our Vx is larger. There is some, and VC1 is smaller. Like, but these two are is almost same. Like, magnitude wise and graph wise, these two graph look like same, but there is some potential drop between these two. Like, this is small, but mathematically, both, if we ignore this drop, like, we can assume Vx and Vc are same, but mathematically, Vx is larger and Vc1 is smaller, but Vx is not much larger than Vc1. Are you getting my point? So our Vx will follow Vc1, and Vx is greater than Vc1, like I explained in this. Like, this is the on condition. Now move to the next part. Uh, so let's assume that Vc1 uh, like Vc1 increases this much, that the M1 not Vc1, sorry. If Vc1 is increasing, our Vx is also increase, and uh, that our Vx increase that much. due to this our MOSFET due to this our MOSFET M3, लाइक इसमें हो क्या रहा है, अगर हम Vx को इंक्रीज कर रहे हैं, तो हमारा Vc को इंक्रीज कर रहे हैं, तो हमारा Vx इंक्रीज कर रहा है, एंड हमारा एक पॉइंट ऐसा आ गया जिसमें Vx इतना इंक्रीज हो गया, लाइक Vx इंक्रीज दैट मच that it push our M3 it push our M3 in out of saturation, or in off state. So for this we can say, for this it push our MOSFET in M3, is it was our MOSFET M3 in off state, that it will make VB, it will make Vx as VB minus VTH, like in this case, like like this case. And for that time, like, if M3 is off, then no current will be there. Like ID3 is 0, so Vy is also 0. sorry, Vy will become our uh, VDD as well. And how VC1 how VC1 looks as like I explained in this, that our VC1 increases. There is no constant slope, no constant charging slope in capacitor. So the voltage rise in the capacitor will look like exponential curve, like this. This is when the capacitor charged by constant current, and it will increase like a ramp, but there is no constant the capacitor voltage rising, and due to this the current entering in the capacitor will decrease as ID1 decreasing. So slope is also decreasing, and as slope is decreasing, that charging is also decrease. So it will look like, it will it will follow this one graph, and then it will follow this one graph, and it will look like I will make this here much more clear. Like first it will it is at some instant, like initially it will behave like a ramp, but uh, this is a charging, DC charging, and this is time. But as current is decreasing, so slope of charging is as well decrease. Like as current is decreasing, charging slope is also decrease. Due to this, our voltage rise also decrease, and it will look like an exponential charging. So it will look like exponential charge. So this our VC will look like this, and same for Vx. But for Vy, what Vy how Vy look like, BC is like look like exponential charge, exponential charging, and same for Vx, as Vx is following Vc1. But for Vy, as t less than 0, it is at a VDD. But uh, at the instant the MOSFET M1 and M2 comes into saturation, as the current hits at T00, as current hits. Uh, so there is some finite voltage drop. There is some current. So there is some voltage drop in R1. There is some voltage drop in R1. So Vy equation will look like this. Vy, which is initially VDD, but when time hit and when the current IRF hit, there is some voltage drop in R1, and the Vy equation look like this: VDD minus R1 I D3, as D3 is this M3 current. So I am writing D3. So and D3 is also decreasing, which is exponential decrease, as uh, because this is an exponential decrease. Like first the current is this, and and it will start decreasing as VC1 is increasing. So it is like an exponential decreasing. So if ID3 is decreasing, then our VY VY will increase. VY will increase exponentially. Are you getting my point? So I will make a final graph, uh, graph as with respect to time. So first I will plot. Let me make it much more bigger. This is our first. I will plot VC1, then I will plot VX, then I will plot VY. This is time axis, and time axis, and then this VY. So how VC1 look like at like at if for uh, t less than 0 time period, it is 0 volt. At the instant of t is equal to 0 plus, it will rise to some voltage VC1, as I mentioned here, like it will attain some voltage VC1. So whenever time hits, whenever and when when will when will this happen? This will happen when this when this IREF flow into M2, as our assumption is this: for time t is t less than 0, simulator doesn't count IREF, but uh, t is equal to 0, it will consider IREF, and from t is equal to 0 plus, it will consider IREF. So okay, so our assumption is this. So uh, voltage is equal to 0, and 0 plus can call a 0 plus, that our capacitor voltage rise instantaneously. Step rise, we can say a step rise, as this is 0 volt, and suddenly it will rise to some voltage, which is step rise. So this is some step rise, and after that it will follow follow exponential curve, which is like this, and it will attain some voltage. And but voltage is this, this voltage, like it will be this, as as what will the maximum voltage it's VC1 achieve, that uh, if we assume that VC1 increase this much, that it will make this MOSFET M1 in cutoff region. So the condition for cutoff region is, and condition for cutoff region is VGS be greater than sorry, for VTH. This is on condition, but for the cutoff condition, VGS is less than VTH. This is our off condition. So our VG is VG is VG1. We can say our VG is VG1, and also this is our. So, what will the VC1 that here? What is the VC1? Which is like this of condition for VG of condition for M1 is that if VC1 increases, and it will attain some voltage, which will equals to VG1 minus VTH, then we can say M1, our M1 is off, and this is the maximum VC1 that our capacitor will attain. So this voltage is this VG1 minus VTH, and this VG1 we can calculate from this current mirror, which is biasing this V2, and this VGS2 is equal to our VG1. And what is this VGS2, which is VTH2 plus 2I ref mu n C over x W over L. So this is some constant gate source voltage, which is here VG1 and minus VTH. So there is one VTH as well. So this VTH2 and that VTH1 will cancel out, as every MOSFET is equal and same. So that threshold voltage will cancel. So our VC1, which will always be greater than or equal to uh, which will become under root under root 2 IRF mu n C over x W over L. So this was the maximum voltage a capacitor this capacitor will attain. So, and for the Vx will follow the same path, like at when t is equal to 0, when t is equal to 0, that that Vx will attain some voltage, uh, which is v which is this one, Vb minus Vth3. So this voltage is Vb minus Vth3, and it will follow exponential curve like V. like uh, VC1, and it will attain some voltage. And for the Vy, at initial Vy, when t less than 0, Vy is Vy at VDD, but but t is equals to t is equals to 0, it will drop significantly and then start rising again, and it will rise to VDD again. This is our final conclusion. Like uh, why this is exponential curve at because the current which is causing voltage drop in R1 register, like this R1 register, it is an exponential decreasing current, and due to this our voltage also increase exponentially. As current is decreasing exponentially, voltage will increase exponentially. That's why this is an exponential curve. And let's move to the simulation, that and we will get a clear understanding of the question. So for the simulation part, this is our simulator. So for the time being, I assume this to be a pulse waveform, but the pulse, let me connect my mouse. So the specification is that my current is 100 microampere. T is delay is 0, rise time and fall time. We have to give this rise time and fall time to be a realistic pulse waveform. If you don't give 0, you put 0 and 0, that you will. If you put 0 and 0 here, that you will attain some. Uh, you will get some corrupt data. So put some rise and fall time, and my t on time is 1 and t period is 2, so and number of cycle is 1. So my pulse waveform is from 0 to 1 second, and I did a transient analysis from only to 100 microsecond to see voltage waveform of VC, Vx, and Vy, and my V bias voltage of this M3 MOSFET is 1, and VDD is 5 volt, and this is my pulse and this is my transient analysis. Let's run the simulation and see the results. So first let me add make it one more plot, one more space, and let's plot. Okay, so I think I have to move my simulator like this. Is Let's move to the simulation. So let's run, and not be I have to select first I will plot to VC at here. So this is VC, and we can see VC like this is a rising voltage, and then Vx here, Vx here, and then our Vy. This is our Vy. Okay, so let's see our results, and we can see that this simulation is running for 100 microsecond, and there is some fixed potential drop here. Like we can see there is some potential drop, not a potential drop, there is sudden rise in the potential of VC, which is around 0.7 millivolts, and the same for Vx, that there is rise of 720 millivolts, and there is difference between VC and Vx, which is of 20 millivolt. So we can say that our Vx is a higher potential as compared to VC. And how is that? I did the analysis. I did the whole analysis in front of you, so you can rewind and watch this again. So our Vx is 0. Our Vx is 720 millivolt, and our Vc is around 705 millivolt. So there is some difference of a 20 to 15 millivolt. And what about Vy? There is some when there is no current, there is some voltage. There is some voltage 5 volt, and then when the current uh, there when there is IRF current in the secondary branch, which is this branch, then it will there is some voltage drop, and our Vy will decrease. Our Vy will decrease to some voltage, not to zero. I said earlier that 0 volt. It will not decrease to zero. To some voltage, it will decrease to some voltage, not to zero, and then rise again. As we can see this, as we can see this in simulation, like it will drop to some uh, 0.0.008, like this is 4.992 volt. Like this drop is very less, as this is our as this is by our parameter we set in this, like this is 100 micro ampere current, not much, and this resistance is 10 kilo ohm. So we can calculate like what will be the voltage drop, as this is very big resistor for this 100 micro ampere current. So that's why we can see that the drop in the current is very less, but there is some drop. That by the point of analysis is this, that there is some voltage drop, and then it will increase, it will rise again to our 5 volt. Like if I fit this zoom, so this will rise again to 5 volt. So this is my analysis, and for this as well, that it will rise to zero. It will attain some voltage 720 or 700 millivolt, and it will rise again and again and again to 1 volt. This was our maximum voltage we will attain in the capacitor, which I calculated earlier as which is V uh, VGS around. So, and this Vx will rise from 0.7 millivolt to some gain, what is this, around 1 millivolt. So this is our Vx. Like there is not much difference in Vx and Vc1, and then Vy as well. Vy will rise to our V 5 volt, as when the as MOSFET M3 and M1, like uh, which MOSFET M1 and M3 will go in the cutoff region, then there is no current, and if there is no current, then our voltage Vy will become 5 volt. So this is my analysis. So I hope you like it. If you have some doubts, you can ask in the comment section, and if I did something wrong, then correct me. And thank you for watching.